এই যে খান জিওটেকনিক্যাল ফোরামে আপনাদের সবাইকে স্বাগত জানাচ্ছি। এই ফোরামে এটি আমার লেকচার নাম্বার 5 and today I'll be talking on settlement analysis for shallow foundations. এই লেকচারটিকে আমি দুটো ভাগে ভাগ করেছি, part 1 and part 2. In part 1 I'll be mainly focusing on immediate settlement analysis, and in part 2 I'll be talking about other types of settlement analysis. So let us see what might be the response of a soil system to a sustained loading. আমরা ধরে নেই যে আমাদের একটি সয়েল সিস্টেমের উপরে একটি লোড আমরা অ্যাপ্লাই করছি, say at time t naught we are applying a load equal to p almost instantaneously, and over the period of time from t naught to onward the load will remain sustained on the soil system. এই ধরনের একটি সাস্টেইনড লোডিং যদি আমরা সয়েল সিস্টেমের উপরে অ্যাপ্লাই করি তাহলে আমরা তার যে স্ট্রেইন রেসপন্সটি দেখতে পাবো সেটি হচ্ছে immediately upon application of load at time t naught, there will be an immediate settlement, immediate strain or elastic strain within the material. Okay, and that is denoted by epsilon sub e. And over the period of time, under the sustained loading from time t naught to onwards, soil মধ্যে একটা creep strain develop করবে, and which is denoted by epsilon c. And beyond creep strain, at a further point of time, due to rearrangement of the soil particles, there will be secondary settlement or secondary strain within the material. On the basis of this understanding, আমরা সেটেলমেন্টের কম্পোনেন্টগুলোকে তিন ভাগে ভাগ করতে পারি। First of all হচ্ছে immediate settlement, which is denoted by S sub E, and quite obviously this is related to the elastic strain of the soil. So immediate settlement takes place as the load is applied almost instantaneously for some soil types, or within a time period of about say 7 days. So immediate settlementটা কিন্তু লোড অ্যাপ্লিকেশনের পরে খুব বেশি আর সময় নেয় না, as the name suggests as well, এবং এটি সাধারণত হয়ে থাকে in cohesionless সয়েলের ক্ষেত্রে এবং আনস্যাচুরেটেড ক্লের ক্ষেত্রে। স্যাচুরেটেড ক্লের ক্ষেত্রে ডিফারেন্ট টাইপ অফ সয়েল আছে, সেটেলমেন্ট আছে। এবং ইমিডিয়েট সেটেলমেন্ট অ্যানালাইসিস আমরা সাধারণত করে থাকি ফর ফাইন গ্রেন সয়েলস ইনক্লুডিং সিডস অ্যান্ড ক্লেজ উইথ এ ডিগ্রি অফ স্যাচুরেশন লেস দেন 90%, অ্যান্ড ফর অল কোর্স গ্রেন সয়েলস উইথ লার্জ কোফিশিয়েন্ট অফ পারমিবিলিটি। যে সমস্ত সয়েলের পারমিবিলিটি বেশি, সে সমস্ত সয়েলের ভেতর থেকে পানিটা খুব অল্প সময়ের ভেতরেই বেরিয়ে যায়, সেজন্যই ইমিডিয়েট সেটেলমেন্টটা কিন্তু সাধারণত যেগুলো হাই পারমিবিলিটি সয়েল সেগুলোর ক্ষেত্রেই বেশি ঘটে। যেগুলো লো পারমিবিলিটি সয়েল, ফর এক্সাম্পল ক্লে, সেগুলোর ক্ষেত্রে কিন্তু ইমিডিয়েট সেটেলমেন্ট হবে, but that will be very insignificant. And the second one is of course the consolidation settlement, which is associated with the creep strain of the material. এবং consolidation settlement আমরা কিছুক্ষণ আগে যে schematic response diagram দেখেছি সেখান থেকে বুঝতেই পারছি যে it is a time dependent settlement and usually it take months to years to develop. এবং সাধারণত কিন্তু একটি স্ট্রাকচার যখন আমরা করি, একটা বিল্ডিং স্ট্রাকচার হোক বা একটা এমবাঙ্কমেন্ট হোক, যেটাই হোক না কেন, 3 থেকে 10 বছর সময়ের মধ্যেই এর যে মেজর সেটেলমেন্টটা সেটা হয়ে যায়। এবং এটি আমরা বুঝতেই পারছি যে it is more applicable for saturated or nearly saturated fine grained soils, যেখানে কিনা আমাদের consolidation theory applied হবে. And the third type is secondary settlement, which occurs under constant effective stress due to continuous rearrangement of clay particles into a more stable configuration. Predominates in highly plastic clays and organic clays. আমাদের যে খুলনা রিজিয়ন যেটা আছে সেখানে কিন্তু অর্গানিক ক্লে থাকে। ঢাকার ভেতরেও বা বিভিন্ন জায়গাতে এখন কিন্তু আমরা মাঝে মাঝে কিছু কিছু অর্গানিক ক্লে লেয়ার কিন্তু আমরা পাচ্ছি। সো এই সমস্ত ক্ষেত্রে যেখানে অর্গানিক ক্লে লেয়ার থাকবে সেখানেই কিন্তু আমাদের রিঅ্যারেঞ্জমেন্ট হবে উইথ দ্য পিরিয়ড অফ টাইম, ওভার এ পিরিয়ড অফ টাইম, এবং সেই জন্য কিন্তু সেখানে সেকেন্ডারি সেটেলমেন্ট আমরা পাবো। সো to summarize, settlement তিন ধরনের: immediate settlement, consolidation settlement, and secondary settlement. Immediate settlement is almost time independent. It takes almost no time. It happens just upon application of load, and consolidation and secondary settlements are time dependent. Well, আমি যেহেতু বলেছি যে এই পার্ট 1 এ I'll be focusing on analysis of immediate settlement. সেটির জন্য অনেক আমাদের যে সমস্ত টেক্সট বুকস গুলো আছে সয়েল মেকানিক্স এর বা জিওটেকনিক্যাল প্রিন্সিপলস বইগুলোতে, you will find number of equations, formulas and all these things. Out of the whole range, আমি যেটিতে সবচেয়ে বেশি কমফোর্টেবল ফিল করি which is based on theory of elasticity and was proposed by Timoshenko and Goodyear back in 1951. The equation is like this. Elastic settlement is equal to, or immediate settlement is equal to Q naught. Q naught আমরা সবাই জানি, this is the contact stress at the foundation level, which is the load divided by area of the footing. So that is there. And B prime, I'll explain what B prime is later on. This is mu sub s, which is the Poisson's ratio of the subsoil layers below the footing. এখানে আমি schematical diagram এ চারটি layer দেখিয়েছি of different thicknesses h1, h2, h3 and h4, and their associated soil parameters like the Poisson's ratio mu s 1, 2, 3 and 4. And the second one is of course the modulus of elasticity es 1, 2, 3 and 4. These are all known parameters. আমরা যারা mechanics পড়েছি তারা সবাই জানে. And alpha is a factor, I'll explain later on, and is is an influence factor for shape, and if is a depth factor, which I'll explain later on. So what is is? Is is a shape factor, and this is given by this expression. And here, apart from mu s, we have one I1 and I2, and I1 and I2 are essentially functions of B and L, okay, and of course the layer thickness. So these are all geometric, the functions of geometry of the footing itself and also the thickness of the layers. So let us go into this M and N first. What is M? M is equal to L prime by B prime. L prime and B prime. Let us talk about this then. L prime, if you are calculating immediate settlement at the center of the footing, the value of L prime will be L by 2. If you are analyzing settlement at the corner, value of L prime will be L. Okay. Similarly for B prime, this is B by 2 for center and B for corner. So M is equal to L prime by B prime, which is described here, and N is equal to H by B prime. H means the thickness of the layers. Okay. So after calculating this M and N on the basis of B prime, L prime and H, you should be able to calculate I1 and I2. And once you obtain I1 and I2, there should not be any problem in calculating the shape influence factor I sub S. I'll go into detail. I'll show you one example problem in the subsequent slides. And the next one is IF, which is the depth factor. Although it is called depth factor, it is the subscript here is F because it was first developed by Fox. So IF is a depth factor which was proposed by Fox, and that was a complete complex differential equation. But on the basis, this is IF is actually a function of depth of foundation, which is here, and also the geometry, the least dimension of the footing, and the long dimension and the short dimension of the footing, and also the Poisson's ratio of the subsoil layers. Okay, so this can be approximated. I mean, the Fox's differential equation can be simplified to this expression, which will also give you quite a good value of the IF factors. Okay, in many textbooks you will find many tables and other things or graphs. I rather prefer using this equation because when you have equation, you can always write a program for this, and that saves a lot of time. You don't have to carry a book and look into the charts or tables every time. Okay, and was talking about this alpha factor. When you are calculating settlement at the center, alpha will be equal to 4, considering the contribution from all 4 quarters of the planned dimension of the footing. And for the sides it will be 2, and for corner it will be 1. Okay, and next let us talk about the zone of influence. Remember, for bearing capacity analysis as well, we considered a zone of influence, and that was equal to the width, the least dimension of the footing. For immediate settlement analysis, suggested by Bowles, that the zone of influence should be considered as Z equal to 5 times B. That is the 5 times of the least dimension of the base. That means we are talking about something like this. So for immediate settlement analysis, you'll have to consider the properties of the subsoil, uh, 5B uh, depth below the footing. Okay, so that is your zone of influence. So everything within this zone should be considered for immediate settlement analysis. There is of course another clause, that is the zone of influence may stop earlier than 5B if the uh, if a layer has a modulus of elasticity 10 times more than the adjacent upper layer. Usually this doesn't happen, but if it happens, your zone of influence can be less than 5B. Okay, let us proceed further. Before we get into real problem solution, we'll have to just a quick recap about the correlations for cohesionless soils and for cohesive soils in terms of SPT value and their description. Uh, we definitely know that if the SPT value ranges from 0 to 4, the soil may be described as very loose soil for cohesionless soil. For 4 to 10, it is loose. For 10 to 30, and so on and so forth. Okay, so very loose, medium, dense, and very dense. Similarly, for the cohesive soils, we have the consistency description, which is very soft, medium, stiff, very stiff, and hard. Please note that for cohesionless soils, we use loose, dense, and all these things. These terms are applicable for cohesionless soil. For example, for sand or for gravel, we say loose soil or dense soil. For clay and silt, on the other hand, we say soft or stiff or hard. Okay. For sand, we do not say stiff. For clay, we do not say loose. So these terms are, when we talk about a loose soil, we automatically understand that we are talking about cohesionless soil. And when we say stiff soil, we automatically understand that we are talking about clay soil or cohesive soils. Okay. And just a quick recap about Poisson's ratio. We know what the Poisson's ratio is. It is a ratio between the lateral strain and axial strain of a material, and these are the common these are the Poisson's ratio of some common materials. For rubber, it is like 0.5. Okay, and for cork, the Poisson's ratio is 0. So these are the two extremes, if you like. Okay, and see where the other materials are. I mean, saturated clay, very interesting. If the clay is saturated, it may behave like a rubber. Okay, so the upper limit of Poisson's ratio of saturated clay is almost equal to the Poisson's ratio of rubber. And for unsaturated or partially saturated clays, this may range between 0.3 and 0.4. Steel, on the other hand, may have a value between 0.27 and zero point 0.3. Concrete point. See here that sand, this is very interesting. Sand has a point ratio uh, between zero point 0.2 and 0.455, depending on whether the sand is saturated or unsaturated. Concrete is 0.1 to 2.2, and the class is here. Okay, let us talk about our soils then. BM Dash in the 7th edition has populated some Poisson's ratio values for loose sand, medium sand, dense sand, silty sand. These are very handy. I mean, you'll have to have all these tables available with you when you are calculating an immediate settlement of a subsoil. And similarly, we have to know the modulus of elasticity, and it is convenient to have relationships between modulus of elasticity and SPT value, because SPT values are more readily available from your uh, soil investigation report, from the board log data. You can always have SPT values, and it is quite convenient to have correlations between modulus of elasticity and SPT values here for different types of soil. For example, if a sand is saturated, then the modulus of elasticity should be calculated on the basis of this expression or equation, if you like, and for a silty sand it should be like this. Okay, great, fair enough. We are almost prepared to carry out a practical problem, and I mean carry out analysis of immediate settlement of a practical problem. And here we have the problem. The foundation is here, which is laid at a depth 2 meter below the ground level, and the dimension, planned dimension, is 2.5 meter by 3 meter. here, and the load that is coming through the column and being transferred to the footing is 1000 kilonewton. The thicknesses of the layers are given here: H1 1.2, 2.5, 4 meter and 6 meter. And the layer 1 has a SPT value of 12, which is a sand, but it is not said whether it is a loose sand or medium dense sand or whatever. We can always go back to our previous tables, and from there we can find the uh, description of this sand, whether it is loose, dense or medium, and on that basis we can pick up the right expression for modulus of elasticity and the Poisson's ratio value. And the layer 2 is a clay sand with a SPT value of 10. Layer 3 is a silty sand with a SPT value of 15, and similarly layer 4 is a sand with a SPT value of 25. And please note that all the soils below ground level, uh, these are all saturated because the water table is up there. Okay, so layer 1, because it is a sand and the SPT value is 12, if you just flicker through the uh, tables I have shown in my earlier slides, you'll see that this is a medium dense sand and it is a saturated sand because the water table is up there. So picking up the right equation for calculating modulus of elasticity and putting the value of SPT here, you will end up with ES1, the modulus of elasticity of layer 1 as 6750 and the Poisson's ratio as 0.33. Similarly for layer 2, you can calculate, just pick up the right expression of the modulus of elasticity and also pick up the right value of the Poisson's ratio from the tables shown earlier. So layer 1, layer 2, layer 3 and layer 4, we have different types of soils in here. The first one is a saturated sand and the last one is also a saturated sand, and others are slightly different soils: saturated clay sand and saturated silty sand. Okay, fair enough. Let us proceed further. We are almost there. So first of all, what is the contact stress or the net applied stress at the foundation level? That should be equal to the load applied, which is 1000, divided by the area of the footing, and that should give you 133 kPa. And the zone of influence, which is very important, and the zone of influence is 5B. So 5B takes you to 12.5 meter below the foundation level, and that means it does not penetrate in the bottom of the last layer. It penetrates about 4.8 meter below the last layer, because if you just add up 1.2, 2.5 and 4, that is 6.5, 7.7 plus 4.8 will take you to the 12.5 meter depth below the foundation level. So it penetrates 4.8 meter into the fourth layer. So that is your zone of influence. So you'll have to consider all the soil properties within this zone, not beyond. Okay. And very much like calculating bearing capacity for multi-layer system, here also we'll uh, calculate the weighted average of the modulus of elasticity within the zone of influence, and that is very easy. So the thickness of the layer 1.2 times the modulus of elasticity plus 2.5 times 8000 plus 4 times 6300 and plus 4.8, that is the amount the zone of influence penetrates into the fourth layer, times 10,000 divided by the whole thickness or the zone of influence will give you the weighted average of modulus of elasticity within the zone of influence. And we are not interested beyond zone of influence, whatever is there. And the average Poisson's ratio, similarly, you can calculate as 0.33. And we are estimating settlement at the center of the footing. So B prime will be equal to B by 2, which is 1.25, and then L prime will be 3 by 2, that is 1.5. M and N are required for calculating I1 and I2, remember, and that should give you 1.2 and 10. And alpha is equal to 4 because we are estimating settlement at the center of the footing. Having said that, we have the value of M and N, and we have all these expressions, so you can easily calculate I1, which is a function of M and N. Just put the values here and do your calculation correctly, and that should give you I1 equal to 0.537 and I2 equal to 0.019, and IS you can easily calculate from this expression. Just put the right values here, and in here for Poisson's ratio value, you'll have to put the weighted average value, which is 0.33. Okay. And IF is equal to DF by B. DF is known, B is known, L, everything is known. So just put all the values correctly and you'll get IF. So that is the summary. Q naught is equal to 133, B prime is 1.25, average, weighted average Poisson's ratio is 0.33, weighted average modulus of elasticity is 8104, alpha is equal to 4, IS and IF we have already calculated. Just put everything in this equation correctly and you will be able to calculate your immediate settlement as 28 millimeter. Okay, piece of cake. Just follow the instructions as I have described and don't get confused. And for anything you need to know further, please write to me in the message. Thank you very much. Thanks for being with me. And very soon I'll post my video lecture on consolidation settlement analysis.